Section 16.9, the Divergence Theorem. So in this section, now we're relating surface integrals to triple integrals. We know that surface integrals are just double integrals. Now previously we've been relating a line integral, which is just a single integral, to that double surface integral. But now we're taking this from 1 to 2 integrals to 2 to 3 integrals. Now, the idea of divergence was first brought up in our video on curl and divergence from section 16.5. Curl and divergence. And you can go ahead and look back at this video if you want a quick refresher. But in general, what we said is that the divergence of, say we have some particle P, or rather not a particle, but let's call this a point P that has an x, y, and a z coordinate. So this is a point in three-dimensional space. And let's say, for example, that I have water flowing out of this point. So maybe this is a faucet, and I've got water flowing out of this faucet, if I'm simplifying this faucet to be a point. Well, the divergence is the tendency of these particles to move away from each other as the water flows, so to move away from this point. So the divergence of this particle might look something like this. The curl of this particle, if we remember, curl is just, with this application, the tendency of these particles to rotate around this point. So our divergence of some function that we can call f, we said is just equal to del dot f. Now we've got the dot product of del and f. Remember, curl is the cross product of del and f. We also said in section 16.5 that we can call the line integral over some curve of the dot product of f and the normal vector n ds equal to the double integral over that domain D of the divergence of f over that area. And this is the exact same thing that we found in 3 dimensions. This surface integral, when we have this capital bold S here, we know that that means we're taking this f and dotting that f with n, the normal vector. And so we found this going from 1 to 2 integrals. We can find this going from 2 to 3 integrals. And so we can simplify the divergence theorem as something we've already seen before, but in another dimension. So going from a curve to a surface to a surface to a solid. 3 dimensions, we can call this a solid. One thing to note here, remember what this is? The double integral over some surface of the dot of f and ds. We said that this was called flux as well. You might see it being called the surface integral or the flux. The other requirement is that E is some bound of a simple solid region. And so this can be something like an ellipsoid, a box, it can be a paraboloid, and really we're only going to be dealing with these simple solid regions. And simple solid just means that, they don't cross over each other, there aren't any discontinuities, nothing crazy like that. And so we can conclude from the divergence theorem that under these conditions, that we can define this as a simple solid region, the flux of f across some surface is equal to the triple integral of the divergence of f over that solid E. And so let's do a couple examples of this. This isn't too crazy of a concept here. We want to find the flux of this vector field f of xyz is equal to zi plus yj plus xk over the unit sphere x squared plus y squared plus z squared equals 1. Now, if we remember, this was an example from section 16.7 on surface integrals. And in section 16.7, we found this to be, well, we know that flux is that double integral over the surface of the dot product of f and ds, which means that this is really equal to the double integral over that surface, and I'm sorry, over that area. We can call that area or that region R of f dot. We know that normal vector in this case is just going to be R, that derivative with respect to u, cross the derivative of R with respect to V. Again, over that area, and this is what we found in section 16.7. But now we have the easier way, because we know that this is really equal to the triple integral over some region that we'll call E of the divergence of f dv, just showing that this is some volume. And so let's start by the divergence of f. The divergence of f is just the dot product of del, which is the partial derivative with respect to x, partial derivative with respect to y, and that partial derivative with respect to z. Dot, and now we have the components of f, which are z, y, and x. Well, the partial derivative of z with respect to x is just 0. The partial derivative of y with respect to y is 1, and the partial derivative of x with respect to z is 0. So this just gives me a divergence of f being equal to 1. And so I'm just computing this triple integral over this region of 1 dv. And this leads us to conclude that our only task really is to, from this point on, find out these triple bounds of this volume. We know this is a unit sphere, and so what's the best way to categorize this unit sphere? Well, probably to use spherical coordinates. And so using spherical coordinates, we want to find our bounds for phi, for theta, and for rho. We know that if this is a sphere, our phi is going to go from 0 to pi. Our theta is going to go from 0 to 2 pi, just to form that entire volume of the sphere. And our rho is just going to be the square root of 1, which is 1. I'm sorry, so this rho is going to go from 0 to 1. And so let's rewrite this as a triple integral of our phi bounds from 0 to pi, our theta bounds from 0 to 2 pi, and our rho bounds from 0 to 1. Our integrand, so what's inside of this integral, is just a 1. Now, because we're using spherical coordinates, don't forget that we need that rho squared sine of phi inside of that integral. And so now this is going to be a d rho, d theta, d phi. And so I can break this up into different integrals in terms of phi, rho, and theta. And so we've got 0 to pi. Well, those are our bounds for phi, and so I'll put sine of phi inside that integral. Sine of phi d phi. We're multiplying that by the integral from 0 to 2 pi of, and I've got nothing in terms of theta, so I've just got a d theta. Finally, times the integral of rho squared, as rho goes from 0 to 1, d rho. All right, evaluating these integrals separately, the antiderivative of the sine of phi is equal to negative cosine of phi. We're taking this from 0 to pi. Now this is going to be a negative. Cosine of pi is -1 minus a negative, and the cosine of 0 is 1. So we have a 2. We're multiplying that by evaluating the second integral. This is just going to give us a 2 pi. We've done this enough. We can conclude that it's 2 pi. And finally, the antiderivative of rho squared with respect to rho is 1/3 rho cubed. Taking that from 0 to 1, we know this will just give us 1/3. And so multiplying these three values together, we get 2 times 2 pi times 1/3, which is equal to 4 pi over 3. And this is exactly what we got from section 16.7. Let's pull this up really quickly. And this is how we did that same exact problem in section 16.7. We took that cross product, then we took that dot product, and then we had kind of some messy integrals to evaluate. So we can see that this method is much, much easier if we can use it, at least in this situation. So let's do another example. Example 2, we want to use the divergence theorem to evaluate this double integral of f ds, where f of xyz is equal to xyi minus 1/2 y squared j plus zk. And the surface consists of these three surfaces. So we've got z equals 4 minus 3x squared minus 3y squared, where z goes from 1 to 4 on the top. So that means from z equals 1 to z equals 4, we're bounded by this paraboloid. So this is our paraboloid. We're bounded by x squared plus y squared equals 1 from 0 to 1. And so this is going to be a cylinder from z equals 0 to z equals 1. So we can see that cylinder. And then on the bottom, this is just bounded by this xy plane, so z equals 0. This is just the xy plane. Now if we were to find this surface integral, we know that this isn't a smooth surface. This is a piecewise smooth surface. And we've got three different surfaces. We've got this paraboloid here, we've got this cylinder, and we've got this circle on the bottom. And so we would have that double integral of S1 plus the double integral of S2 plus the double integral of S3. We can see how difficult this would be to integrate. Really just kind of painstaking here. But if we write this as a triple integral of the divergence of f over this volume, well, isn't this all one volume? So if we can easily find the bounds of this volume, it's going to make our lives a whole lot easier. And so let's start by finding the divergence of f, which is just equal to del dot f, and we've got f being equal to xyi minus 1/2 y squared j plus zk. So just taking really each of these partial derivatives. Partial of xy with respect to x is y. Partial of negative 1/2 y squared with respect to y is negative y. Partial of z with respect to z is 1. And so again, we're just left with 1. Now this is not always going to be true, so let's just put a note here. It just happened to be true for these last two problems. But the divergence of f is not always 1. This was just a coincidence. Okay. Just important to point out there. And so now we've got this triple integral, again, of 1 dv. How do I categorize these bounds? Now, in this last problem, this region was the unit sphere, and so we know we needed to use spherical coordinates. But how can we categorize this surface? Well, here's my hint. Because I see this cylinder, this part is a cylinder, I'm probably going to use cylindrical coordinates. So if I use cylindrical coordinates, I've got a z, I've got an r, and I've got a theta. Now what about z? We know that z starts at 0 because one of our bounds is z equals 0. And then if I want to kind of draw this arrow, I know it's bounded on the top by this paraboloid. And so this goes from 0 to 4 minus 3x squared minus 3y squared. But the problem here is that we said that we want this to be in cylindrical coordinates, because then when we get to x and y, we would have something that's kind of messy. And so can't I rewrite this as, let's move this other stuff down. And we can call this 0 to 4, and I'll factor out a -3 because then I'm left with x squared plus y squared. And isn't x squared plus y squared just equal to r squared? And so I can rewrite my z bounds as going from 0 to 4 minus 3r squared. Great. Now I know that my r just goes from 0 to 1. This cylinder has a radius of 1. And my theta is just going to go from 0 to 2 pi because I want one full revolution around this z-axis. And so my coordinates are going to be 0 to 2 pi, 0 to 1, and 0 to 4 minus 3r squared. Now because I converted to cylindrical coordinates, I need this r. So this is going to be r dz dr d theta. So starting with the innermost integral, taking the derivative of r with respect to z is going to be rz as we go from 0 to 4 minus 3r squared. Plugging in 4 minus 3r squared, we are going to get 4r minus 3r cubed. So now we've got the double integral from 0 to 2 pi and from 0 to 1 of 4r minus 3r cubed dr d theta. Now at this point I don't see any thetas, and so I can split off this integral from 0 to 2 pi d theta times this integral from 0 to 1 of 4r minus 3r cubed dr. I know from 0 to 2 pi, the integral of 1 d theta is just going to give us 2 pi. And we're multiplying this by, when I take the antiderivative of 4r, I get 2r squared. Antiderivative of -3r cubed is -3/4 r to the 4th power as we go from 0 to 1, which is equal to 2 minus 3/4. 2 minus 3/4 is 8/4 minus 3/4, which is 5/4. And so for our final answer, we're multiplying 2 pi by 5/4. We get 10 pi over 4, or 5 pi over 2. And that is it. And so this should be a little bit of a refreshing lesson. Using the divergence theorem, we can break down a series of several surfaces into one solid just to make this integration a whole lot easier. And that is it.